How do big ride-sharing services like Uber and Lyft scale their systems? In today's video, we'll find out. Let's go. So in today's system design video, we're going to take a look at how Uber and Lyft scale their systems. So how they design their systems to serve millions of customers at the same time. Compared to search engines like Google and social networks like Facebook, those companies and those kind of services are fairly new. So they were facing sort of unique challenges when they were starting up. And both of them grew extremely fast. So it's very interesting to take a look at how they achieved what they have today. Now, one quick thing before we start here. Recently, I launched successintech.com, where I offer mentoring and coaching for exactly those kinds of interview problems. We cover system design, algorithm design, and also behavioral interview questions. And if you're interested in one-on-one Skype sessions with me, go to successintech.com and see what I can offer you. Now this time we are going to take a little bit of a different approach. In my other system design videos, we talked about 2 or 3 features and dove deep into those. Today, we're going to do the following. We're going to take a look over the whole architecture and think about all the things that services like those two need to operate. So we're not going to dive deep in any of those. We just mention them, list them up, and think what those implicate. And then we're going to dive into one of the core features, which is quite an algorithmic one, less system design one. But as always, we'll start with 2 to 3 core features of those services. Because whenever somebody asks you to design a system like this, so the interviewer will be like, how would you design Uber? How would you design Lyft? Then that's such a broad question that you need to focus on a couple of core features and then design the system around those features. Now, in the case of Uber, start thinking what Uber actually does. Of course, Uber does things like payment management, star ratings, or some kind of other customer feedback gathering. But those are things that lots of services on the internet do. And these are things that, of course, are important to the system and important to Uber and Lyft, but not the core features. So the actual core features of a ride-sharing service like Uber is finding and matching customers to drivers. So this is the first one. And then the second one is around the mapping and routing. So mapping in the sense of you open up your app, you see a map of the city you're in, and you see a map where you can see yourself and all the drivers around you. And as soon as you click on one of those drivers, or as soon as you request to get picked up, you will get a ETA, so an estimated time of arrival whenever that driver, which was matched to you, comes to your location. So broadly said, the second core feature has to be mapping. Now, to support those 2 core features, we need to think about how Uber operates and offers a platform for all the engineering teams. They certainly started working with those, but we can always think about the foundation, the lower layer of everything first, if we want to. So that helps and gives you some sort of a starting point. Now, what is the lower foundation? What is the lower layer? Most of the time it's storage, some sort of infrastructure storage. Now, what do we need to store for those 2 services, for those 2 features? Definitely all the trips, right? So trip storage is one thing. Why is storing all the trips the customer have taken important? More or less because it's the base of everything. It's the base of Uber's business. So they need to know how customers use their service, but it's also the base of all the drivers, right? So they want to get paid. So whenever they take a customer somewhere, the trip in all its details and as precise as possible has to be stored somewhere in a database. So Uber in reality uses multiple different cloud providers, at least that's what they did until 2 or 3 years ago, but they also use own data centers. So they leverage cloud providers like AWS or Google Cloud Platform, but they also have their own dedicated data centers replicated across the world. So what they actually do is they store each trip in at least 2 data centers. And the primary data center they store the trip is as close as possible to the city where this trip happens. So trip storage is in a closed data center and a backup data center. So what does that mean? Whenever somebody starts a trip or finishes a trip, trip information will be stored in the primary data center, which is, let's say the city is London, somewhere in the UK, right? If possible. Now, it could very well happen that this data center is for some reason offline. And what happens if it's offline? Well, the trip is just getting stored in the backup data center, which for the UK may be somewhere in Europe. Now, when data center 1 gets online back again, they try to sync those 2 data centers up. And this is not an easy task to do, but the most important thing is availability. And in this case, availability is guaranteed because we have 2 data centers. If both of those data centers are offline, then we'll get into a problem with availability, because if the customer would start to request a service or start to request a pickup, then the trip couldn't be stored in any of those data centers. So in the worst case, in the worst case, that trip wouldn't be stored anywhere. Talking about those 2 kind of data centers, we could also try to think about what kind of databases Uber uses here. So what is the goal of those 2 databases or data centers? We probably want to have high availability, and because so many trips and requests for pickup happen at the same time, we need to have very low latency calls to those data centers. Trips themselves are quite low in relationships to each other, because every trip is like an independent atomic unit. And so what comes to mind are NoSQL databases. Now, Uber in reality uses a mix of SQL and NoSQL databases. They developed some sort of fork of MySQL, which operates schema-less. But they also, for example, use Cassandra as a low latency database. Now, continuing on the thought of storage, this is something we need immediately. So whenever people are using the app and whenever people are taking trips, data gets stored in here. Another point of view on storage is analytics data. So data Uber is mainly interested in whenever they want to find out how to make their service more attractive to customers. So what many companies do is they have something like this as a running and 24/7 running database with low latency, but regularly, periodically, they store and archive data somewhere else in a data warehouse mainly, because on those data warehouses, they can run big expensive queries to find out about trends in their service. So a service like Uber is mainly interested where people are using Uber and where maybe there are not enough drivers. But at the same time, they could be interested in trends regarding dates and time of day. So those are things they can find out with a data warehouse. I'm gonna call it DW here. And we know that Uber uses Hadoop as a data warehouse. So, archived into Hadoop to run more expensive queries. This part is decoupled from this one. So let's say the data warehouse or parts of it are offline. This would affect the ability to run queries on the data warehouse, but it doesn't affect daily business. People would still be able to, take trips and rate their drivers and make payments. So this is something we need to point out. We want to have a decoupling here. This is replicated, this is highly available and is very fast. This one doesn't have to be that fast because it's not used in daily business. Okay, what else? We have real-time data here, we have data warehouse and business analytics up here. Whenever we have a big service that needs to be available and is highly available for many million customers, we need to think about some sort of caching layer. So a layer where data can be stored closer to the customers and probably on some sort of in-memory database, which is a lot faster than storing things on spinning disks. It's easy to say we need a caching layer because almost every time we need a caching layer, but we need to think about for what purpose we can use this caching layer. So if this is something like static data, which we deliver to many customers in the same form, a caching service, a cache itself is very effective because we can have more of them closer to the customer. We can pre-warm them, so we can put stuff in those caches before customers use them. So before the customer, for example, opens the app, and customer here and here and here, they use the closest cache available. But things like the position of drivers or live data is very hard to store in caching layers. So chances are that, let's say the position of a driver, to store it in a caching layer is not the best way to do it because it's making things more expensive. The positions change so quickly that you would need to store it in a caching layer and then send it to the customer, compared to store it somewhere in an in-memory database, for example, like Redis, and then directly send it to the customer. So what we could store in a caching layer are things like map data, like where are points of interest on a map, or also event data, so something is happening on a particular location for a couple of hours at least. Now, lastly, talking about storage, we need to think about logging. In the case of Uber, logging is something extremely important because we need to know which driver was at which position doing what at any point in time, so to say. It's interesting from a business perspective because we want to know how they move and how we can make their ways more efficient. But it's also interesting from a legal perspective because what happens if an attack on a passenger happens? We need to prove how this happened and where it happened, things like that. So there needs to be a logging layer somewhere, and logging needs to be as real-time as possible. So whenever the event happens and somebody wants to look at it, time in between those two has to be below a couple of minutes, even better a couple of seconds. Now, logging happens from endpoints. So endpoints in this case are apps using driver apps, but also user as a customer apps. So if we say we have a couple of people on apps here, so this could be a customer and this could be a driver, and we have many more of them, there needs to be some sort of a layer and a service used for ingestion of all those logs. So we have many small messages, log messages, like the position of a driver or the position of a customer coming into this log system, and it's probably smart to also replicate this system. So this is what Uber is using for Kafka. So Kafka is a service which is able to ingest lots of messages in real time and gives you the guarantee that none of those messages are lost. So they in reality use a cluster of many different Kafka servers which synchronize in between each other. And so this is Kafka. And it's a cluster of those Kafka instances. Now, Kafka is very good at ingesting those data, that data in real time, but at some point they need to store it and archive it somewhere. And that's what they also use Hadoop for. So this Kafka cluster periodically at some point in time does the storing into Hadoop. So now we have a pretty complete picture over different kinds of storage they're using, but you could also ask yourself now, where are the actual applications? Where's the business logic in all of this? Now, what we need to know about Uber, but also companies like Amazon or Google, is that they rely on service-oriented architecture, an SOA. You'll read this a lot of times, SOA. So what does that mean? There's lots of literature on this topic, and there are many people who say it's the best thing in the world, and others who say it's not the best in the world, so to say. But just to give you an idea over SOA, the feature, the core of this idea is to have many smaller services, which are either just working internally, so inside of the company, or have an external facing interface. They mostly just serve one purpose. So instead of having a big monolithic system or a couple of big systems, there are many smaller services which are decoupled from each other and can also live and be stored independently. So just because one of them is offline, the others don't have to be offline. This is a service-oriented architecture. And companies do very different sorts of service-oriented architectures. Now we know that Uber uses an SOA, and we need to think about where do we put all those services? Where is the application logic? Where is the business logic? It's not that one service lives on one machine and serves all of Uber. The goal is again availability. So a service lives on many different machines and in many different regions. So those are geographical regions which are as independent as possible from each other, and they serve customers in that region. So the difficulty of this approach is to keep all those services up, because if it's just a handful of services you need to keep running, it's easy to have a person, so manual intervention. Whenever a machine goes down, a system administrator could go there and reboot the machine and reboot the service, so to say. With thousands of services on thousands of machines, that's impossible. So the keyword here is provisioning and keeping the services running. So provisioning means that machines or containers oftentimes are getting started automatically, and the provisioning step is getting the software, so all the packages, all the codes, onto that newly started machine or container. Now let's see. Let's get rid of this SOA here for a second. And let's forget about the caching service for the moment. So we talked about different regions where many different applications live. So the green application, I'll just call it app 1, lives here, but also in another region. And this app 1 inside of this region, in reality, it's simultaneously running on many different machines. All those machines have to be updated, rebooted from time to time, and need to be kept running without or with as less as possible manual intervention. So we said this is a region. So this is maybe North America, and this is maybe the European region. Now, provisioning is the step to get code and get applications on those hosts on those machines. So there is some sort of repository where the code lies in static form, and the provisioning step gets us from static code to running services. Furthermore, we know that for provisioning, Uber uses a tool called Teraform. And they probably use containers. So with containers, you hear Docker a lot of times, and Docker is a tool which allows you to pack your service into a container which is shielded from all the other containers which are running on the same host. So for the service you develop in this static code repository, it feels like it has a whole machine, it has a complete Unix system on its own. In reality, many of the same Docker container run on, for example, one host, but they're completely independent of each other. So this has many advantages because it's just one container which feels like a separate host is running. You can reboot it without affecting other services. And as I said, Docker is the solution many companies are using nowadays. And I'll just write some of those down. There is Docker. And then another tool Uber is using, which is very popular, is called Mesos. And Mesos is something which manages the collaboration and the interfaces between all those services. So it checks if services are still living, and it starts new ones and shuts down other ones. It checks that there are no malfunctions and no errors, and it manages the life cycle of all those services during runtime. Okay, we now know how static code gets on all those machines, and now let's say those services are ready to serve customers. There is one more big problem which needs to be solved. In order to get an app which a customer is using at this very moment, in order to get that app connected to one of those regions, there needs to be some sort of logic here. How does the app connect with the backend? Which backend should it connect to? And which instance of this one service it should talk to? So this is the problem of routing and networking. Whenever we have a complicated setup of many different services and many different hosts and regions in place, we need a pretty sophisticated routing service in front of all this, so that customer requests are getting distributed to many different machines. So we don't want to have all the requests on just one host, for example, or one region. They need to be distributed as efficiently as possible, and this routing mechanism needs to be very smart and needs to know about the state of each application. So if there is state, so data and the state of a customer request, is if there is state involved in one of those services, the customer needs to be redirected to the same host or the same instance. Now, this is the reason why many internet applications and internet services are being developed stateless. Stateless means there's one request going to a service and an answer is coming back, a response is coming back, and the communication is ended, so to say. The customer or the server doesn't need to know about the state of this conversation with the service. So being stateless allows you to develop services which are hosted on many different machines, so many instances of many machines, and a customer request can get routed to all of those. So for example, at point in time 1, it gets routed to this region, And 1 second later, the second request can get routed to another region. And because there's no state involved, so there's no memory here and here, they don't need to communicate with each other. Everything happens in this one request going back and forth between server and customer application. Now our picture here gets more complete, but we haven't talked about testing yet. Now, of course, they're using unit tests and a suite of integration tests, but let's focus on one topic here. Whenever you have a distributed system like this, where you have many regions, many services which depend on each other, and services which are linked and chained, now what you need to think about is how do your services operate in case one of them fails or one of them is offline. Now, this is the topic called resiliency. So, what happens if parts of your system are not working for a certain time? What Uber is using in this case is a tool they call Hailstorm, and Hailstorm goes to a random set of services or hosts, and it more or less turns them offline, so it shuts them down. While they do this, they know lots of things can happen, so you don't need to do this in production, for example, but you can do this on so-called shadow fleets. So shadow fleets are groups of hosts where the same services are running in the same way, but they don't serve the customer. They get customer data, so they get, for example, all the requests coming from drivers and customers, but they don't connect with those customers directly. They just get the same data and they process the data and call all the backend services like the production services would do. Now, if you run those shadow applications, if you run those shadow fleets and you start breaking things on purpose, you will be able to log and observe how your systems work in the case of a failure state. So this makes your systems more resilient because you find out what needs to be fixed. Oftentimes, those service-oriented architectures are so big and they're like a web, like a network of many, many smaller systems. People start to lose the overview over them. They don't even know that your service relies on some service you don't even know about, because there are so many services you rely on and they rely on others that you don't realize that if something in the backend breaks, you will be affected too. So Hailstorm is what they use for this purpose. And there are many open source projects in this area, and you don't even need a tool for this. You could also just operate on a shadow fleet and start turning off your services yourself, right? You could have some sort of a 12-hour period where you try to turn off data centers or databases. You maybe close connections and see what happens. And if things break, that's a very good sign that you need to fix it, because it could break in production as well. I promised you to get into one of those topics in more detail, and this is something whenever you hear ride services like Uber and Lyft, it's the one big computer science topic people want to hear about. So Uber, as almost every mapping or routing service somehow, is a graph problem. So what does that mean? A graph problem, exactly what you know about from university. Graphs, or let's say maps of cities, are graphs in reality. So you could model a city with edges and nodes, and a node, for example, could be an intersection somewhere, and an edge could be a street between two intersections. Now, Uber and Uber's core service, namely mapping and routing of customers and drivers, is a graph problem because they do multiple things with maps. First of all, they take your location or the driver's location, and they give him a route to you. So let's say a driver gets assigned to serve you on his app. He will see a route to where you're waiting for him. This routing, which for example if you use your phone, Google Maps does for you, is something which is pretty complex, because we know from computer science that the so-called traveling salesman problem, which is mapping and finding out which is the shortest route from one node in the graph to another, is an NP complete problem. So these are all terms which are very fundamental in computer science, and nobody expects from you to solve those kind of problems in a system design interview. Especially with this one, they're more or less unsolved. So it means there is no really efficient solution for those kinds of problems. But it's good to know about them, and it's a really interesting approach that different ride-sharing services use to solve those problems. What I also mentioned is the traveling salesman problem. Okay, so what do we want to achieve? Uber had one big challenge, which was getting very precise ETAs. So ETA meaning how much time will it take for you to get picked up by a driver. So the driver is here, you are down here, and the streets could look like this. What does that mean? This is a city. This is a city map, and the city map will get mapped to a graph. So intersections are our nodes. And all those streets connecting the nodes are edges. When you look at a map and you want to find, or if you look at the graph and you want to find the shortest way from one node to some other node, in that case from D to A, you need to calculate different options and you look at which one is the shortest. Now, if you want to integrate things like speed allowances, so let's say on this road you're allowed 60 kilometers per hour. On this road it's only 30. How do we solve that problem, How do we get that data into the graph? Graphs can have some sort of an edge value, an edge weight. So if we say 60 kilometers per hour is more favorable for us because it's faster, it allows you to travel faster from this node to this node, this edge here will have a lower weight. Now, whenever you do calculations with algorithms like Dijkstra's algorithm, this edge will be favored against edges where you're not allowed to drive as fast. So calculating this is not that big of a problem because you can do it, you can pre-compute it. You know all the speed allowances on those roads, so you just calculate all the different possibilities in a city map, which is a pretty huge problem because there are many intersections and many streets in each city. But as long as this stays like that, and normally they do unless there are some construction works going on, you can pre-compute it, okay? So you pre-compute, and whenever a customer is at this node and the driver is at this node, you will already know that, let's say this here is the fastest way or the fastest route from driver to customer. And you will be able to tell the customer ETA, let's say 6 minutes. Okay, fine. What are we forgetting here? We have static data, we pre-computed this data, and we can get customers an ETA. But those ETAs will be pretty much worthless because traffic situations can change very fast during the day, during different seasons. There can be construction work, there can be snow and different road conditions. So we need to integrate traffic data into those calculations. Now, Uber can use their own apps, and people are using those apps. They have them on their phone. They can use location data to track their customers and track traffic situations in the cities they operate. This is not exactly the problem. The problem is giving ETAs to customers in real time. Because I mentioned this traveling salesman problem, so calculating routes and calculating durations is an NP complete problem. It's really inefficient to do those calculations. The graph itself changes all the time. So in our cheap version, our easy version without traffic, we knew that this edge has some sort of a weight and this edge has some sort of a weight. But now, including traffic information, the edge weights will change all the time. Because now, for example, this is the slowest one, and this edge could be the slowest one, and we would need to take this road to the customer, for example. As we know today, Uber gives you quite a precise ETA, and also Lyft gives you quite a precise ETA when you open up the app. So how did they do it? In reality, what they rely on are two main things, and I'm sure in the meantime they developed a lot more sophisticated versions of this algorithm. But in the past, they relied on historical data. So they looked at the situation you are in. So imagine you're the customer and this is one of the available drivers. And they want to match you with one of those drivers, probably one of the drivers which is the closest, but also one of the drivers which has good ratings. Now, you open up the app, and when that happens, they look at past situations. So they look into a database, and because they have so many trips in their databases and they know exactly where this trip started, so where the request happened, where the drivers at this moment in time were, they search for a similar situation in the past. So that means historical data for ETA calculation. Now, this ETA calculation can get you pretty precise because probably there was somebody at your position and a driver at this position here some time ago, but maybe it was even at the same time of day and traffic was similar at that day, but probably not exactly like today. Maybe the traffic was similar, but this road here is closed in your situation, and back then it was not. So it's good, it's a lot better than just relying on static edge weights, but it's not perfect. So there's another problem, and the biggest problem with this approach is you need millions of data sets, you need to store millions of trips, and you need to be able to look them up very quickly. If Uber or any ride-sharing services operates in a city for many years, or for at least a couple of months, they record all those situations and they make them available for those ETA calculations. But what happens when they just start out in a city? They launch a new service in whatever city. They don't have any past records of those kind of situations. So they try to make a lookup when you, for example, just request a drive from your house, but they can't find any because they maybe just operate in your city for a week or two. So they're doing a second thing. They're doing a fallback approach, or let's say they merged ETA calculations from another approach. What they do is NP complete calculations. So they use an algorithm which is based on Dijkstra's algorithm or A star, also something very interesting to look up. And they calculate ETAs with that. Now I just said it's too slow, right? Yes, it's too slow to calculate all of the city with those algorithms in real time, but they segment the city. So they recalculate smaller parts of the city, and they interpret a small part of a city as one graph. And as you can imagine, if you need to calculate ETAs for all kinds of different situations, let's say for all possibilities in this graph, and the graph has only like here like 5 or 6 nodes, you can do it really quickly. So they came up with an approach to split the city in many different smaller parts which are as independent from each other as possible, and they recalculate those smaller parts, those smaller graphs in real time. So the solution to this ETA problem for them was relying on historical data, and second of all, splitting the city in small independent parts, recalculate in real time in those smaller parts. So splitting and then using a graph algorithm. Now, how they did the splitting is very crucial to this, and I'm not exactly sure if there is literature or there is knowledge about this outside of Uber, but how to split the city graph in smaller parts is really important, because if there is traffic in this part of the city, this traffic influences and impacts neighboring parts of the city, and it's not easy to make independent grids or independent smaller parts of a city. So they need to have a very sophisticated algorithm in place to come up with those smaller segments of cities. But if you look at this, it makes sense, right? They know they can get really precise ETAs with an algorithm like this, but it just takes too long. So they use both of those approaches and they merge them together, or they use either one of them if, for example, historical data is not available. Now, to finish this off, let's circle back to our initial core features we talked about. We talked about mapping right now. We know that mapping is a huge thing for Uber and all those services which deal with maps and routing. So we know how they do ETL calculations. We know they use different open source maps and open source routing frameworks and libraries, but they add a lot of their own logic. So mapping, ta-da. And looking at this, we just realized that customer and driver matching relies a lot on this mapping technology. So solving the mapping part of Uber solves customer driver matching to a big part, because the main influencing factor for you as a customer is probably how fast you can get from point A to point B, and that includes how fast somebody can get to you and pick you up. So solving this in a reasonably good manner will get you a very high satisfaction rate on the customer driver matching. What also influences the customer driver matching, of course, are things like cost. And then there's also the aspect of ratings. Okay, let's recap this really quickly. We talked about storage, different sorts of storage, different kinds of storage. Talked about scalability of business logic, scalability of services. We talked about getting those services connected to the customers. We talked about logging and business analytics, data warehouse topics. And then we dove into the computer science part of this core problem that Uber is solving with this graph explanation. If you want to know more about those topics, which is very recommendable if you interview, or even just if you want to be a better computer scientist, a better programmer, developer, whatever, look into graphs in general. Like there are many easier graph algorithms, but also looking at algorithms like Dijkstra's. Those are really not that difficult, but it's really neat to see how they work out and how they can be more efficient than others. Now, I'm sure we didn't cover everything a service like Lyft needs to operate, and we didn't solve any actual problems here, but at least we now know what the problems are and how we can approach them. Don't forget to subscribe, and don't forget to visit successintech.com for one-on-one sessions with me. My name is Roman Lopez, and this is Success in Tech.